Дорогие дамы и господа, разрешите вам представить доклад на тему Novel Geometries and Layouts of Double-clad Fibers for Fiber Lasers. My name is Pavel Peterka. I come from the Institute of Photonics and Electronics of the Czech Academy of Sciences here in Prague. And now let me switch off the camera so that you can see the whole screen. I was very much looking forward to meet you and visit your fiber laser laboratories in Novosibirsk. Unfortunately, it is not possible due to the pandemic. I would like to point out here shortly one particular reason for my interest. It is the fiber laser cell sweeping, where you have done really excellent pioneering results in discovery of this effect. For those who are not familiar with cell sweeping, you can see this effect in this real-time movie. It is a spectrum of ytterbium fiber laser of similar setup like this Fabry-Perot laser with mirrors formed by cleaved fiber ends. The laser wavelength is continuously and slowly sweeping from about 1072 nanometers to 1082 nanometers and then jumps back. It is a special case of longitudinal mode instability. The longitudinal modes coherently lace one by one. More famous is of course the longitudinal instability regime, where the modes are locked a different way around. They oscillate also coherently, but at once, in so-called mode-locked regime. Not only longitudinal modes of the fiber can be unstable in this direction. We may observe also instability of transverse modes, as it was discovered also around 10 years ago in Jena. Both instability regimes are driven by dynamic fiber gratings. Fiber Bragg grating in longitudinal mode instability case and long period grating in the transversal mode instability. Longitudinal mode instability is also a pulse regime. But in contrast to the mode-locked regime with ultra-short pulses, here we have long pulses, typically on microsecond scale. See the oscilloscope traces here. But with higher pump power, the pulses may evolve into chaotic train of nanosecond pulses with kilowatt peak power. So it was a reminder of something we have in common. But nowadays in our laboratory we are more focused on development of fibers. So that's why I choose topic of my lecture as a review of our recent work in double-clad fibers. After short introduction, I will show you our approach to numerical modeling of coiled and twisted double-clad fibers. And you will see results on two cases in stadium fiber and GT-wave fiber bundle. I will mention spiral coiling, and finally I will show you some experimental results on our CO2 laser apparatus for shaping of preforms. So the double-clad fiber is an efficient transformer of low-quality beam coupled into the broad inner cladding, and it transforms the energy to excellent laser beam quality emitting from narrow core that is doped with rare earth ions. In double-clad fibers we have two families of rays of the pump. One group is the so-called skew rays. They propagate around the core and never cross it, so they cannot transfer the energy of the pump to the core. The other group is meridional rays. They cross the core and transfer the energy from the pump to the laser signal. In fact, circular fiber cross-section is the worst case for the pump absorption. See the red curve here. At the beginning, meridional rays have good overlap with the signal core and transfer the energy to the signal. However, as they get absorbed, we have only skew rays that they do not mix with the meridional rays, and so we got saturation of pump absorption. To eliminate skew rays, fibers with irregular shape of fiber cladding were developed. In the first optimization step, we look for such a cross-section that provide proportional absorption with fiber lengths. So, in ideal case, pump absorption is given by the ratio of core area and cladding area, and it is proportional to the absorption cross-section in the core of the core. However, this is valid only for ideal absorption, and in most cases it is far from reality. Nevertheless, some people tend to use this formula to build their fiber laser. This is one of typical misunderstanding of principles of cladding-pumping. So in the first optimization step, we look for optimal cross-section that provides homogeneous, it means constant absorption along the double-clad fiber. In fact, it would be nice to have different absorption at different places along the fiber. For example, at the beginning of the fiber where the pump is launched, we would like to have low absorption in order to minimize the heat load of the fiber at this place. So more sophisticated further optimization involves tailoring of absorption along the double-clad fiber. Many different fiber cross-sections have been investigated. For example, this spiral cladding cross-section proposed by Kuznetsov and Molyneux was found particularly efficient. However, most theoretical optimization of pump absorption was long time restricted to approximation of straight fibers with no bending. Bending and twisting was used in experimental optimization of pump absorption by mode-scrambling. Typically, mode-scrambling was achieved by figure-8 spooling with or without twist. So here this is picture about twisted figure-8 layout. Very ingenious method is changing the convex and concave spooling in the so-called kidney-shaped spooling. Indeed, such smart coiling method may lead to significant improvement of pump absorption and overall performance of the fiber laser. What is interesting, it works well even for the case of double-clad fibers with circular cross-sections. Holger Zellner presented in a conference both experimental studies and theoretical modeling. He was a rare exception because he took into account fiber bending. He used the so-called WKB approximation. It is a combination of ray tracing optics, from this we get a trajectory of the ray, and wave optics. From this we get phase and transverse distribution of the model field. From now, we would like to show you pump absorption calculated using rigorous modeling by beam propagation method, BPM, either based on finite element method or by FFT methods. Fiber bending is taken into account by modified refractive index approach. Later, we extended this model in order to include also the twisting of the fiber. Because when you have fiber that is coiled on the spool and simultaneously twisted, the structure of the fiber rotates with respect to the spool. As the structure rotates with respect to the spool, then the modified refractive index also rotates with respect to the fiber. So we are rotating the modified refractive index also with respect to the fiber. So rotation of the modified refractive index profile around the structure mimics the twisting of the fiber. Here you can see movie about pump absorption in a hexagonal fiber for the straight, bent, and simultaneously coiled and twisted geometry. The fiber is always illuminated by a speckle pattern that mimics the electromagnetic field in the pump pigtail with 105 micrometer diameter core. First millimeter of propagation is shown somewhat slowed down, and after 1 millimeter the movie runs faster. In all cases, pump becomes spread over the whole area of the cross-section, but in the case of bent fiber and bent and twisted fiber, the pump field is somewhat squeezed. Here in the bent only fiber, it's squeezed in the outer edge with respect to the spool. The straight and bent only fibers have a bluer center as the pump is depleted, thereby absorption. However, in the bent and twisted fiber, the rotated corners of the hexagon effectively mixed effectively mix the pump, and there is not a blue center in the middle. Lower pictures show longitudinal section at the fiber going through the fiber axis. So it goes through here. The cut goes through here. You can see here. So the spool is at the top of the figures here, here, and here. In the straight fiber, pump is spread over the whole cross section. And you can see the blue line in the middle. In the case of the bent fiber, the pump is squeezed to the outer edge of the fiber, and in the case of coiled and twisted fiber, again the pump is squeezed to the edge of the fiber, but it traverses through the core as it goes down the fiber. We have experimentally verified enhancement of absorption in twisted hexagonal fiber doped with thulium. Here you can see the preform with hexagonal shape, and this is the drawn fiber with thulium doped core. We measured the pump absorption in coiled fiber. This is the black line here, and the pump absorption in simultaneously coiled and twisted fiber. And we got quite significant difference at the pump wavelengths of 793 nanometers, of about 8 dB for the 3 meter long hexagonal fiber. This test was done with halogen lamp, broadband halogen lamp, but we have tested it also by using pump laser diode at 790 nanometers, and we got similar results of pump difference between the coiled and twisted fiber. Then we tested it also in laser. So what about the laser performance? So does it help also in this case for fiber lasers? It is really hard to test. Imagine that you have 125 micrometer fiber, so it is always somewhat chaotically bent and twisted when you work with such a fiber in the lab. Only when it is spooled carefully in factory conditions, you can expect some proper, regular geometry of the fiber layout. So we made the following two things. First, we cut fiber that is much shorter than the optimum length, so that the pump absorption enhancement would be pronounced. If the fiber is too long, so that everything is absorbed, all pump is absorbed anyway. And secondly, we hanged fiber to the ceiling first day, and we have introduced a tension by attaching a little weight to the other end. So by this, we hopefully to eliminate some memory of the polymer coating, and the fiber becomes straight again. The next day, we put down the fiber from the ceiling and we did the laser tests. So one mirror was attached to the pump end. It was a fiber brake grating, highly reflective, and 1951 nanometers. And this is the multimode fiber as a pigtail from the laser diode. The other mirror was a perpendicularly cleaved fiber end with about 3.5% reflection. First, we measured the straight fiber laser output, then we coiled it carefully without introducing any twist, and then we coiled it and twisted it. We got this laser curve. And in fact, we got 50% increase of slope efficiency when we compare the slope efficiency of the straight fiber and the coiled and twisted fiber. It's not very practical to twist fiber that is already drawn. So to twist coiled fiber, it's not very practical. Better way is to twist the fiber during the drawing. So if the preform is rotated during drawing, the twist becomes frozen in the final product. Look here in the absorption curve. This narrow red curve with red dots is absorption of coiled fiber with no twist, and we got about 10 dB absorption of about 1.5 meter long fiber. Look here for the absorption of the same fiber, but that is twisted during drawing. We got at least 6 dB improvement in the peak absorption. So, in conclusion, the preform spinning improves pump absorption in double-clad fibers with the octagonal cross-section, even for the case of straight fibers, or in coiled fibers with large radius of the coil. Next two examples are closely connected with pump and signal combiners. So first, let's have a quick review of the combiners. Obvious method is bulk optics. It was used already in the first cladding-pumped fiber laser developed by Elias Snitzer. One can add a dichroic mirror so that a single-mode laser signal can be added. However, we missed the beauty of all-fiber alignment-free configuration. Highly practical is the star combiner that combines a ring of pump fibers around signal fiber. Double-clad fiber can be end-pumped by direct splicing of pump and signal fiber. So, there is no need for a combiner at all. But it is better to have a double-clad fiber with cross-section similar to the input fibers, like the stadium here. The second group is side pumping scheme of combiners. The beauty of this combiner invented by Gapontsev and Samartsev is that the signal fiber goes through the combiner and the model field of the signal is almost unchanged. You can couple pump from the side of the fiber by using some refractive or diffractive element like the V-groove here. Successful side pumping is also the so-called GT wave structure with multiple individual fibers bundled together. Pump and signal fibers can be spliced directly to the double-clad fiber. Here you can see pump fiber with core of 105 micrometers. This is the black circle, is the pump core, and this is the standard single-mode fiber. It can be spliced with low loss to a double-clad fiber with cross-section that resemble shape of stadium. Standard fusion splicer can be used. We need only special holders with flat bottom. Pump absorption in stadium-like fiber depends a lot on the pump launch conditions. So whether the pump enters the fiber far from the spool, at an angle to the spool, or at a position close to the spool. The best absorption, the thick red line, very close to the ideal limit, we got for the twisted fiber. In this graph, you can see the pump power fraction in the core, so it means it is called pump overlap with the core. The thick red line stands for the twisted case, and it has an oscillatory character below the ideal pump overlap. You may think that such theoretical guidelines may help to improve your experiment, but in this case it was a bit the other way around. First we draw a stadium-like fiber, but this fiber was really ugly rocking when it was drawn. My colleagues did not like it at all. Fiber orientation with respect to the spool changed several times per meter, like here in the twisting case. So my colleagues worked hard to improve the drawing conditions. When I got new fiber that was drawn without the mistake of instability, it means without rocking, I got very poor performance of lasing. But the first case, with the rock fiber, it laced quite well. So, twist or rocking of the fiber helps to absorb the pump in double-clad fiber. We developed the theoretical model only after, so that we can explain the beneficial behavior of the twist. Completely different in principle is the GT wave double-clad fiber bundle structure. It is a multi-fiber arrangement. It is not a single fiber, and the pump coupling is distributed along much longer lengths of the active fiber than in all the other cases. The GT-wave structure has at least two fibers, one for pump and the other for the laser signal. Look at the cut where the pump fiber and the signal fiber is spliced to the loosened ends of the GT wave. The pump and signal fiber are twisted either after drawing or preferably when the fiber structure is drawn from preforms at the drawing tower. Twist is important to keep the fibers together, but also the twist is important for efficient pump coupling, as we have seen before in the part of pump absorption. It is nicely supported also by numerical modeling, while only negligible absorption we can observe here in the green line for straight fibers. We got a very efficient pump absorption when the fiber bundle is twisted. See the blue line here. Short amplifying modules with a length of about 10 cm were fabricated using rare earth doped phosphate glass fibers with high concentrations of active ions. It has great advantage for short pulse amplification. It works in medium power levels of up to about 10 to 20 watts. Here we see a cross-section of double-clad fiber for almost 10 kW single-mode diode pumped fiber laser. It has 8 pump parts that surrounds the central part with the core. It is another example where pump absorption is so important, and it is tailored along the fiber. So at the beginning, the pump propagates still around the central core, so we have a lower pump absorption where the pump is high, and the pump absorption is increasing along the fiber. So far, we have seen coiling in kidney-shaped and figure-8 spools, and more thoroughly we discussed twisting of the double-clad fibers, like hexagon and GT-wave fiber bundle on a standard cylindrical coil. One more special coiling we see here. It is the spiral coil, either pumped from the inner part of the spiral, or here you can see the dashed line spiral that is pumped from the outer part of the spiral. Look here for the absorption graph, and you see that the octagonal and hexagonal fiber got almost the same overall absorption, but there is different absorption rate along the fiber. So when you pump it from the outer part of the spiral, you got smaller or slower absorption rate at the beginning of the fiber and higher absorption rate at the end. And this is rather advantageous, because at the pump side of the fiber you should have lower absorption. It means you have lower heat load. And on the opposite, at the end, you need to get rid of the pump so that you do not lose too much useful pump in the cladding mode stripper. I would like to mention also theoretical work about stadium coiling. It is somewhat similar to the kidney-shaped coiling. It was done by, the theoretical calculations was done by Men Gyeong-hu while she was in the National University of Defense Technology in Hunan. And another case is a tapered fiber amplifier, where the heating effects are mitigated at the pump end thanks to using a thicker fiber. Final part of my paper is devoted to preform shaping. Here we see a hexagonal preform made by standard grinding and polishing. We developed a thermal shaping of preforms by CO2 lasers. The CO2 laser beam coming from here is focused on the preform that moves below the laser horizontally. Silica fume is sucked and collected into the collector pipe, and when one groove section is finished, the preform is rotated and another groove is polished. This technique allows shaping preforms with concave and convex structures. It offers short time of process, depends on laser power, and it is a fully automated process. can see a couple of cross sections of drawn fibers. So hexagonal with shallow grooves, hexagonal with deep grooves, octagonal or decagonal cross section. In summary, we have presented rigorous theoretical modeling why pump absorption is enhanced by broken circular symmetry of inner cladding cross sections, namely for hexagonal and stadium fibers and for GTA fiber bundle, and by unconventional coiling methods. So in detail, we treated twisting for hexagonal and GTA fibers, and we shortly noted also spiral, kidney, and stadium shapes of the spool. But we should remember that non-circular fiber shapes do not help for mode mixing in strictly straight fibers and bend-only fibers. And we pointed out importance of pump squeezing and decentering effects. We discussed also approximation of cladding pump absorption given by core absorption cross-section and ratio of core and cladding areas. This formula is often used by numerical modeling and quick design of fiber lasers, but we should use it wisely. It is only an approximation. In fact, the truth is the opposite. The overlap factor is never constant along the fiber. Only for some geometry it can get close to the ideal case. And with this, I would like to thank you for your attention.